that you had to really spend these 24 hours and work on these tasks. And even we are tired, so we can only imagine how tired you are after these 24 hours of hacking. So how does it really work is we have presentations from 6 top teams.
First of all, congrats to these teams for having made it, and congrats to everybody else who has been fighting until the last minute.
So how we will proceed is that we'll have presentations by the 6 teams, starting from Team Coffee Break, then Prestige Gorilla, the White House, Viking Team, Polar Nut, and Seaweeds. So we have presentations from most of you. Still, we need presentations from Prestige Gorilla and the White House. And also we need the code from you. So please send the code, and then after these presentations, also all of us from the CISPA team will meet, and we will discuss the solutions to find out how well you did.
And an important thing about the presentation is that you have 6 minutes to talk, and this is a fixed deadline. So like there's no 6 minutes and 1 second, there's 6 minutes and then it's done. And I will be sitting there and taking the time, and I will signal you when 2 minutes are gone. So if you're presenting task 1 for your team and you see this, it means like your 2 minutes are over, and any second that you go over that, you're taking the time from the presentation of the next task. So try to just not accumulate too much of a time depth, so to give all of your teammates a chance to present the 3 tasks in a row. And then after the 6 minutes, we will allow questions. So there will be questions to your solutions. And yeah, we're just curious to hear how you solve the task.
So just we don't want you to repeat the tasks. All of us know what the tasks are. Just I think to make sure that those of you who just would like to have some reminder, so or work on other tasks. So you had 3 tasks. First task was data reconstruction.
And in this task, it was about reconstructing training data, and we let you submit 100 reconstructed images. We matched them to the closest one in the training set, and then we calculated the mean squared error.
Also, a second task was model tracer. So the goal was to attribute a given image to its source. So we had the 9 classes. We gave you 9,600 images, and we asked you to classify each image from one of these classes. And the metric was accuracy, given number of correct predictions over the number of all the predictions. And finally, the task from Torsten and then also Jonathan.
Yeah, the final task was about finding chimera images, which are images that have a different prediction depending on the platform where they are executed. And the score here was like a discounted effectiveness score. So the more images that was found, the better. But when you found a chimera, we wanted to have them very close to the original images.
Okay. So now we can start the presentations by the teams. So we would like to first invite here to the stage the Coffee Break team. So how it works is you can use this clicker. So just to move the slides, and also we have the recording for you. So. Also, are you going to speak?
Yeah, I'm going to speak.
You're also going to speak?
Okay.
Then I'll hand this one to you.
Can we start? Hello everyone, we're Team Coffee Break, and we're representing the University of Oulu from Finland. We're Yumish and Lee, and this was our approach to most of the problems. So it's like we either want to do the lazy solution or like over-engineer a giant like model. So we did both, and let's look at the solution. So for the first one, the task was to minimize the mean squared error. So how do we minimize the mean squared error? If we just take the mean of the entire image and send one single color, then we get we exactly like nail the mean. So we got like 0.40. score just by sending like the average of all the pixels for each image. And after that, to improve it further, we did some basic like k-means clustering and just blended matching images. So on the second one, you can see like multiple images have been blended. And we also tried training like a proper model, like with the over-engineered approach, but the score didn't go up. So like at the end of the day, the lazy approach worked better. And for task 2, it's a similar thing. So it was supposed to be like a white box problem, but if we just ignore the white box part and just treat it as a black box and just try to predict like based on the given data, we tried that. It didn't quite work, but so it overfit the data and it just sent everything as an outlier. So all the images, we just sent it as an outlier, and that gives us the score of like 0.425, and that's like, that was our score. So everything is an outlier. For task 3, we added some noise to like the test images that we were given and try to like find like the gap between the two functions, like in that image, which kind of worked. We got one, which is basically like a little bit of noise on that. So when it gets like tokenized and like goes through the encoder, it's basically the same thing. And that gave us a score of like 3.13. So the lesson learned is that lazy problem, like lazy solutions work. Yeah, that's about it. Thank you.
Thank you very much. So maybe also yes. So any questions?
Yeah, thanks a lot for the overview. I have one question to the Chimera. You presented like 3 different ways. Did you combine these, or were there 3 different approaches?
We did do all 3 approaches, but we couldn't find any. Like the pipeline we used was really slow. Can we go back to the previous slide? Yes, so we did all 3 approaches, but the pipeline was really slow. And to analyze one image, it took like 5 to 10 minutes. And we ran that overnight, but in the morning we didn't have any results. So that's it. More questions?
I'd be curious to hear more about your clustering approach for the first part. So you were saying you were clustering something, right?
Yes.
Could you go into detail?
The clustering is it's not that deep. We just find similar looking images and just cluster it. So like the raw pixel values.
In your own reconstructed images already, or from the candidate set that you got, or?
From the candidate set we got.
Okay, so you get the candidates like the 1000 and then you cluster them to have similar images and
yes, and just overlay them like on top of each other.
Okay.
Yeah.
Makes sense.
Okay, any more questions? Also, if you have any questions in the audience, feel free to ask. I know some of you were really curious how others solve the tasks. Okay, so if no more questions, thank you so much. Okay, so we would like to invite the 5th team.
Yes.
Okay. So, is team Prestige Gorilla here? Okay. You send the slides or you don't have slides?
You sent it.
You sent it? Okay.
That seems to be seaweeds.
Okay. So who's gonna speak? Quick. So we have to do that. And this is
Thank you so much. Yeah, hi everyone. My name is Yunus. I'm with Suyash and Nicholas. Our group is called Prestige Gorilla, and today we're just going to talk about our hackathon experience. So we can start off with just firstly stating that we did take a research-oriented approach. So we first prioritized research before anything, before experimenting or conducting any code. So that's what we would like to state first. So to begin, we have this 3 tasks that we each split up. And so we start with the first one, which was more like cracking a pixel vault. So when we first began, the AI model did have a lot of issues that we would like to point out. So one was that it was outputting pixels with a mean intensity of negative 0.65. And because of this, the hidden target in the dataset, which we noticed to be something called cipher, was was having a mean of 0.47. And this brightness gap was something that we identified, and we figured that it was something that we could solve. So there were several aspects actually that we could use to solve this, including the distance, the brightness, and other features of the picture, such as how blurry it was and other different features. So one way we used to solve this was by running a script, which not only scraped the leaderboard to find which features affected the pictures the most, but also identified which ones were impacting the score the most. So by doing this, we not only singled out which features were affecting each picture the most, but also which ones were impacting it the most, so we could single them out. Another thing which we did was to consider the data pipeline. So one thing we did was take 5 times over the sampling strategy. So instead of generating 100 images, we generated a pool of 500 candidates. And this allowed the classifier API to act as a classifier, which only chooses images that best match the target. And apologies. But we can move to the next task. Would you like to?
Yes, and I can talk about task 2. Task 2 was about identifying which model version was generated by a given set generated set of images. So we obviously use the white box approach to extracting the signals. We computed a negative log likelihood of each image, and under all the 8 models, and a double description consistency score. Then we combine this, the data. The feature extraction process was quite lengthy, and this was probably the biggest problem for us in this step. And this ended up being the longest bit. After that, we used a simple classifier, a likelihood classifier, and calibrated an outlier threshold for the validation. After that, we were still not satisfied because the outlier, the outliers were being chosen far more frequently than normal. So we tried to fix that using some hyperparameter tuning. But in the end, we were able to submit a score which we were pretty high confident with, although quite close to the end. But yes, I can pass on for the next task.
Right, so our third task was the chimera task, where we had to identify chimeras, which are essentially modified versions of images that are nearly identical, but have can cause different mathematical calculations, meaning the same model can calculate a different output from the same input, depending on its hardware. And we attempted to use quite a standard and researched method for identifying these chimeras by sort of entering the general vicinity of the chimera, and then focusing in on the instabilities in the backend. And initially the script was very slow and it didn't identify chimeras very effectively. However, we optimized it over time to identify chimeras pretty effectively. And so we had to calculate we had to try to identify chimeras with very minimal perturbation between the things. Anyway, yeah, that was task 3, chimera task. Thank you.
Okay, any questions?
Hi, thanks for the presentation. Could you maybe explain a bit more about the optimization that you performed for task 3?
For task 3, yeah, so initially it was kind of very much an ad hoc sort of approach. We kind of freestyled the approach using our own method without looking at sort of the research methods. But then, yeah, we tried to use sort of like finding the boundary and exploiting the backend instability later, and also like the other team mentioned, adding sort of noise to create these chimeras.
Yes, I can add a bit quickly to that. Initially, we were struggling with identifying chimeras, so we kind of just focused on, instead of focusing on identifying chimeras with like a small gaps, we focused on just purely identifying chimeras, so we could at least make some progress. Eventually, then we started. We came across this approach where we would focus on the boundaries and focus on identifying, adding some disturbances near the boundaries, and that's where we would try to identify chimeras.
Also, in your solution, you mentioned that you found a boundary. So, could you please give us some information how you managed to find this boundary and also exploit it to find your chimeras?
Yeah, so we essentially found the boundary by identifying an image and then adding a little bit of noise and stretching, comparing and stretching the output of an image. So that, yeah, sorry.
Thank you.
Okay, any more questions? I'm just asking curious one more question. So regarding task 2, how did you extract features from the images?
So,
Sorry, could you repeat the question?
How did you extract features from the images?
Features from the images. Forgot.
yeah, we mostly try to use whatever help. This wasn't like the domain of our strong domain, so we tried to get what help we could. We researched about it, and we tried to get the help of like LLMs and try to do that. And that was mostly the way. Again, we tried to do the research. We did not understand it fully in time, but yeah.
Okay, thank you.
Okay, so we have now the next team, which is the Viking team.
Thank you so much. She will stop.
Hello. Hello. Hello everyone. We're at the Viking team and we're going to present our task 1, 2, and 3. What we did with our task is like we distributed each task with everyone and then we discussed each task. So that's how we came up with our solutions. We can...
You.
Yeah, okay.
Okay. Good. Yeah. So our problem was we were provided with like 5,000 images and training images, and what we had to do was like find the images that was closer to the training images, and we weren't given the data of the training images, so we couldn't see the training images. What we did for our solution was we first divided the data set into like 100 images, so like different batches, and then we took those and then we calculated the logic, and then for each if you could go, yeah, and for each logic we calculated the highest logic for like every image, and then we saw that we calculated we had a list of the highest logics, and from there we calculated the top 100 images, and from there we compared those images, and then we saw which images is the model most confident about. So that was our goal, but that was more like the initial goal. But another approach that we took was like we checked for like the mean, the margin as well. So the second approach we took was like how much the top 2 values of the logic for each image, because that also tells us like, okay, this is which image is like most closer to the training model. So that's another approach we used, and also like the confidence tells us which resembles the training data most. This is our whole yes, and we can go to task 2.
Yeah, I think the problem solved everyone know. Can you move? Slide. Okay. Yeah, actually we have faced the key challenge was is a limited label trained data we have it. It's we need to generate the strong generalizations. So the critical components are reduced to OOD, actually out of the distributed detections. So which one? No, can you back? Yeah. Actually, what we have discussed with the team, how we are going to implement this one. Initially, we have discussed, and we have basically we are trying to implement the feature-based attribution pipeline using the pre-trained ResNet of 101 backbone. First, we have tried with the ResNet of 50. Instead of that we have approached ResNet net using the black box testing. We have approached more predictable data. So first we have a start 2048 dimensional embedding for all the image. For the model attribution, we have contributed that class centroid training embedding of the 8 known the generators. How this will work? What you have minimum guarantee we have. I try to approach this one. The centroid based classification group for the small training that we have. First initially we have trained the small data, and the confident based able to prevent the force miscalculations of image classification. So we have approached this balance attribution as a OOD detection. In the summary, the combined the pre-trained deep embedding and the centroid similarity scoring and validation that tune the OOD of thresholding features.
You have 1 more minute for the
Yeah.
last task.
Okay, so this task was pretty daunting for us at the beginning, but so how we approached is like so I'll not explain what is Chimera and all. So like how was our high level pipeline? So initially we were facing issues when we were going through the images because we didn't find any chimeras. Then we needed to do some pre-processing. So then we thought of doing like a phase approach. So in the first phase, we are just pre-screening all the images. And in those images, we are just feeding it to both of the models. And then we are finding one logic. And then based on that, we are calculating the further scores. And whatever the current logic which we have found in the first pass is the first chimera which we have actually found. And in the phase 2, which we are just refining, and so we took a greedy approach. So for each and every image, we are increasing and decreasing or changing the image by 1 plus 1 or minus 2 pixel. And then we are comparing, so each image we are generating 6,000 images. And then based on those 6,000 images, we are again feeding to both of these models. And using this approach, we were able to find the chimera in this case. And then there is one more thing we need to do.
Okay, I think you're done.
Okay, so we also use L-square refining.
Awesome.
To refine the file.
Thank you.
So, any questions?
Thanks for the presentation. One question for task 1. So you mentioned how you screened the training data to find basically ones with the highest confidence. So did you stick with this approach, or did you also try to change them, like to apply noise or change them anyway, or did you just always try to just leave them as they are?
So we tried shadowing. So like we were trying, not shadowing, we tried the smoothing of the images. So but the problem was we were not doing everything like smoothing them in the center all the time. So we need to make sure that we smoothen them more in the center, and at the edge we need to leave them as it is. So this is something we also found, and we also tried this approach as well.
Okay, thank you.
You also presented 2 approaches for the first task. So do you know which one was the one that gave you the best scores eventually?
Yeah, it was the
Task.
margin.
Margin.
That
Okay.
we went with.
Yeah.
Makes sense.
Any more questions? The assist of Steiner and everywhere. Any questions? No. Okay. Thank you so much.
Thank you, sir.
I don't
Sorry.
So now we are inviting the White House.
Thank you. All right. So, hello. I'm Vlad, and today I'm with my friends and colleagues, Alex and Sherban, and together we are the White House team. So I will start by presenting the first task. So in the first task, we basically went through the papers, and what we saw is that you can attack this type of black box classifiers with auxiliary data by constructing an inverted model. So what we did is we took the auxiliary data set, we got the logits from the black box classifier, we constructed a CSV with predictions, and then we tried to map the predictions to the photos. So this task is pretty hard because you cannot really map like 1 by 10 vectors to 32 by 32 by 3 images. So what we did is we took these 1×10 vectors of probabilities and we basically made them into an image. We shuffled the pixels and we created a big image, so the function is less surjective. All right, so the next slide. So yes, this is the exact idea that we used. So this was the black box classifier. We took the predictions, we truncated the unimportant features, because we also discovered that there are 5 important features in this data set, and we fed them into an inversion model. This was, as I said, it was pretty simple and it gave pretty good results. I think on the final leaderboard we were like actually a bit lower, but yeah, that was the main idea of the task. Okay.
Okay, now for task 2, we played a lot on the validation dataset at first. The first idea was to use a classifier to assign ImageNet classes to each of the image, because we've seen in one of the papers that this is an advantage when attacking this type of models as opposed to LLMs, for example, that their code generation is constrained by these classes. So we needed the classes, and we ran also the test dataset and the validation one through this classifier. Then we ran them through the encoder. So we use the encoder as the inverse of decoder, which, as we've seen in one of the papers, is not the best idea. We also tried to use an inversion model to use as an inverse decoder, but that didn't work well in the end, so we stick to the encoder. And yeah, then we computed the negative log likelihood for next token to be generated by that model, as given basically in the repo for each photo and each model. And then we plotted the results to observe some patterns. So these are for the VAR. We've seen there very low is actually the outliers, which is the thing that was mentioned in the paper, that because the encoder is trained on actually real images, yeah, so here lower is better. So we would have expected the VARs to be the lowest, but actually it's the outliers that are the lowest. But also we can see that in each group of VAR, the correct size is basically well defined, and for RER the same. Yeah, so then we inferred this heuristic. So we were looking for outliers in the VAR chart that we've seen before, and then used for RER the difference between the best one and the mean, and yeah, then we just fine-tuned these parameters using the validation data. We did this computed matrix, maximize the accuracy, and then apply the same thing on the test data and process it.
Thank you. And now for task 3, I'll get to it pretty fast. So our first approach and just our first step would literally just be like to have a certain back-end function, the math library that is trying to get a certain image very close to a boundary, so that there are the chances of it being classified as 2 labels are pretty much equal, and afterwards we are getting the 2 models, or a model 2 times that has 2 background, how do you say, math libraries, and these 2 are getting into a tag war. Each one of them is trying to make the image be classified as a certain label. And after we realize that this tag of war just makes the image have the same 2 labels over and over again, so it's either on one side or the other side of that hashed area. We're just making a grid search through all the pixels. Afterwards, the next optimization that we did was to literally parallelize the code in the way we like to do so.
Yeah, thank you.
And that's it. Thank you very much.
Presentation. Any questions?
Could you please go back to the previous slide? And you have written that you have tried to do gradient descent with two math libraries. Could you please explain us how did you do this process?
Yeah, definitely. Like, it's pretty straightforward. It's literally doing it with one library, computing the gradient, modifying the image, and then verifying how close is it now to the border. Is it more towards the first label or the second label? So we have the two math libraries. One of them is pulling towards label A, the other one towards label B. If now we see that we are more towards label A, we ask the math library that's doing towards label B to take action to modify the image.
So do you update the image itself like this? Yes. And why do you use gradient descent?
To keep the image right at the border of the two labels. Gradient descent is basically just computing the way to modify some pixels in order to make the image have another label.
And also you specify you consider a specific label. In the camera examples, you don't really care about which label it is. You only want to be the two math libraries give different answers for the given image.
Yes.
So, is there a specific reason you consider a specific label?
Well, to be honest, we consider all labels for each image. At first, we try to take the label with the highest probability and the second label with the highest probability. This is pretty useful because you don't really modify the image that much. But when we went to the tug of war part, we realized that both the backends of the models were just fetching that image very far away from the initial one. If you understand, yeah?
Thank you.
Thank you.
Okay. Just one more question. So how did you compute the scores within the RAR family or VAR family of models?
The scores meaning like the negative log likelihood or?
So you have this nice algorithm, yes. So,
oh yeah. Yeah, so.
Next slide, I suppose?
Sure.
Yes. So so how do you compute the best RAR model or the best VAR model?
So we just compute the negative log likelihood for each running the image to each model, and then best VAR model is basically the minimum of these values between VAR 16, VAR 20, 24, and 30. Yeah. And for RER, we use the mean because we observed that usually when it is actually an RER image that went through, the minimum value will be far away from the mean value of the others, while otherwise they were usually all around the mean somehow. It's probably not the really most accurate heuristic, but yeah, it went to pretty good results.
Okay, just one more question regarding the first task. So how did you find these 5 most important features? What do you mean by them?
Alright, so in training the inversion model, we used the auxiliary data, only the auxiliary data because we didn't generate anything. At first we thought that the auxiliary data is generated, but actually the training images were generated, so yeah. So we just did an input on the classifier and we got predictions, and what we saw is that the mean over some labels were actually very close to 0. So I don't know what they are, but I knew that they were 5. So for example, 0 was one of them. The mean of 0 was very, very low. Like, I don't know.
Okay. Thank you very much.
So now we also have the second team. So we would like to invite PolarNat to the stage.
Is this a... I still need to hold this. It's double.
Okej. Vänta om man går fram och tillbaka.
Yes. Okay. Hi, we're Team PolarNat. We're from KH and Umeå University. So for the first task, we applied the inv-align approach, which we got from the SOK paper you showed, as it had very low MSC for data reconstruction. You already know the basic architecture, but it's like an autoencoder where we train the decoder, which is the inverse model. So how we train it is we get the logics from the auxiliary dataset, and then we train the decoder, a transpose CNN, to reconstruct the image with MSC for the original image. And it's similar for the testing, then you feed in some logics and you get reconstructed images. So how did it go? And these are some of the images that were reconstructed. We started with some black images, or very, very dark ones. Then we got some contours, still bad reconstruction because we had kind of a bit error on the loss. Then we got stuck really long with the same image generated, something weird happened, until 11 a.m. this morning when we got some proper reconstruction with quite low loss. So how did it go? We submitted it, but it didn't really increase the score, but we still got some nice reconstructions. So what would we do next? One obvious thing is the point 2 actually, which is that we were submitting reconstructions of the auxiliary dataset, which is not the aim here. We want to submit the reconstruction of the training data that we don't know. So for example, we can generate some more data samples during for the what is it called? Infinity dataset, and maybe fix that issue. We also want to work on maybe fixing the unrepresented classes that we found. Yes.
Okay, so we basically tried to reduce task 2, which was model attribution, figuring out which model generated the image. We basically reduced it to the problem of if we have the class of an image, which model generates it, or which model is more likely to generate it. So we start up there, basically take the image, give it to ResNet, get the class of the image, and in parallel, we also tokenize it using RAV and VAR models and compute the reconstruction and quantization losses. We use the class of the image and those losses to basically extract class conditional negative large likelihood, or NML. We built a few features, like it's tons of features based on this NML, and then train and run a 9-class logistic regression. And it's 8 class plus 1 class for the outlier, which gives us the source model. Should I?
No, sorry, Marius.
Sorry.
So for task 3, this was, as you may have experienced, a very difficult challenge. We took the route of implementing the algorithm 1 in this paper, and with a caveat actually, fixed a few bugs, and then we scaled it up so we could run over 1,000 kind of processes at the same time to actually find a lot of chimeras once it got working. So how did we do this? First, we reparameterized the pixel values so we could have more fine-grained steps when doing gradient descent. We, as in the paper, we used a 2,000-step warm-up with only one backend to be more efficient before moving on to using both backends simultaneously to compute the gradient towards two different target classes, right, and move the image towards the boundary. We had a dynamic step size alpha, and one difference from the paper. In the paper, they picked the target class by picking the true class on one and then a random class on the second. We calculated that there was 90 possible ordered pairs for each image, meaning over 90,000 image optimizations to be done, which required a lot of scaling. One challenge that we had was that the feedback loop was very long, meaning that we didn't know if the algorithm would work until last night at 3 a.m. when we got the first Chimera. After that, it was just about scaling, and to do that, we had 2 workers in an container for each library, basically running a lot of processes. Questions?
Yeah, thanks a lot for your presentation. I have one question for the Chimera challenge. You mentioned a warm-up phase, so what does it mean?
So the warm-up phase just means that we don't do the tug of war with both backends. We just use one backend, moving still towards the decision boundary. And that's because in the beginning, the differences are so big that the differences between the 2 math libraries don't really matter. So we can still take big steps more efficiently with just one backend.
I have a question for task 1. So you mentioned that you used Infinity to generate images, right? So could you elaborate a little bit on what exactly you queried with, or how exactly you did this?
Okay, so we did not have time to do that, so that was more the next step. So one idea is that, all right, so we're reconstructing the auxiliary dataset now, so that's what we're submitting. So that's not the training dataset. Instead, we want some like more general images to feed through the decoder, and maybe this will be more close to, yeah, we have more samples basically, and then we can, by having more samples, we can get the higher probability by classifying them again. And then we can choose the highest from them to send back, as in like trying to get more closer to the the training data set by looking at the probabilities. I was also thinking, or we were also thinking that some classes were not represented in the auxiliary data set. I don't know if that's the true distribution, so maybe generating more images would also kind of fix that problem.
This question from the audience.
So you mentioned that you created 2 obtainer workers for per image when you were trying to find the chimeras. How do you manage to avoid the backslash? Because we did exactly the same, and things were not very happy. I was seeing humongous queues from our team.
Yes, if you can go back to the maybe, so what we created is various shards, and then these are basically processes, and every process is responsible for, let's say you have 100 images, 1,000 images and 50 processes, then every process have both backends, so every process can spin up, so these shards are basically one obtainer. So every obtainer has possibility of spinning off 2 prop backends, right? So what happens is that if you have 1,000 images, 50 processes, then 20 images, everyone gets a responsibility of running exactly at the same time. And what we did is that first talked about the initial warm-up. So basically, in the first, we didn't have any overhead in terms of, because we were just treating a model. Only one backend. So within one backend, we kind of gravitated towards the boundary as soon as we were satisfied with either number of iterations or a threshold set, how much we want. And based on that, then we went back to start looking at 2 backends. But when we did 2 backends, what we did basically, we did a shared file IO. So in that case, we were just like 2 processes running at the same time that they were communicating, and there was some moderation of those writing to the same file and taking input and output. So in that case, we kind of avoided spinning up and down of containers and a lot of other overheads. So that's sort of kind of worked out in some ways. That was kind of one implementation, but he also did another. So we were kind of working kind of.
Yeah. Okay, thank you. Any more questions? So I think I have a question to task 2. Could you describe more, elaborate more on these different features that you use for this task?
Yes. So some of them were quite obvious. For instance, quantization and reconstruction losses, and also per model NLLs. But the problem was that when we used quantization losses in isolation, they basically didn't work, or they didn't produce like enough test set in the little board. So I tried to combine as many features as I could in classifier. And where did I get the idea for these features? Basically asked ChatGPT to give me some ideas for brainstorming.
What is the meaning of for code?
Which one?
The second one to the left. Second to the left.
In the left. So it's basically quantization and reconstruction losses. But because we have, and this might have been true, I miswrote the number.
Okay. We can move on. Thank you so much.
Thank you.
Did it have another?
One, yeah.
Right.
Thank you. So now we have the first team, Sivit. Please come to the stage.
Oh, sure. Is that a microphone? Yes. I see. Hello, hello.
This is for our recording. This is for the
Right. Oh, yeah. Okay. Fair enough. Yeah, that's okay.
Okay, so 2 minutes per task.
Right. Hi. I'd like to start by introducing ourselves. We're Seaweeds because it sounds like CVE, and we're EV Nordquist right there. Recent dual degree student, recently graduated bachelor's, KTH, working with Nordic. Yes. AI guy. We have Ankit, master's, recently graduated, like about to graduate from the ICT program. We have this crack guy, ETH. Do I need to say more? Me, I could not find a job, so I got a PhD, robotics at KTH. Right, let's move on. 3 tasks. Let's not touch too much on exact task descriptions, but yeah, go on, boys.
All right, so task 1. In task 1, we wanted to reconstruct specific images. Now, images of the same class, of classes, my brain, sorry. Of classes with low intra-class variance, images of a class with low intra-class variance, they are closer to each other in the image space, making them look quite similar. And this also makes them easier to reconstruct. Now, if you look at this example between dogs and ships, you can see that dogs, they look quite different, quite varied. Whereas ships, they all kind of have like this blue backdrop and maybe more like rectangular shapes. So this was our approach to this problem, our initial approach. We locally computed interclass variability for each class, and then chose the classes with the minimum variability as our starting points, or focus points, for these classes. And then it turned out that the big hero behind our score was the class of ships, and more than later. Okay, so a little bit about our approach to this task. we did not just only work with auxiliary data. We actually also created our own data using the Infinity 2D model. Yeah, we called it every 10 minutes since there was an API limit on getting logins for it. Then we stored it in kind of like a shared data pool. And using this data, we were able to create a surrogate model of the classifier. So kind of like a model that tries to mimic the classifier's decision boundaries. Yeah.
And so once we have this data, we can get logics and everything, and then we can expand the data set. What we do is that we use this inverse alignment approach, and we use the surrogate model instead of this API and the inversion model to minimize the reconstruction loss. And this is something that helps us with the performance.
So basically, instead of doing one API call every 10 minutes, we said, fuck it. We'll call the API, we'll train our own mini model, we'll learn how it works, and we'll crack it that way. Okay, there's a quick progression of how our scores evolved over time. We'll not touch into that too much. Second task, model tracer. 2 approaches. One intelligent, one dumb. Guess who did the dumb one? It was me. I said, fuck it. Images, CNNs, try to classify. Did not work. What we managed to do was the following. We managed to discriminate between var and rar, but we could not discriminate between different sizes of vars and rars. The intelligent stuff, the intelligent boy.
Okay, so basically what you have here is we want to do the paper that we got from the reading list, but we don't want to make it too difficult for ourselves, so we're not going to actually like re-implement the whole thing. But Michael here actually pointed out when I explained the paper to him, what about that box? That looks all suspicious. That one is, you don't have to do anything, you just have to encode the code, and then you can just check the reconstruction. And so that's what we did essentially. However, you might have a question, well, what about they're just different depths? Like there's 2 VAD and RAR, they're just different depths, they have the same codebook and so on, like why, what about that? Well, what you can do is you can add auto-arrested negative log likelihood, so you can just check how likely the image is under the model, and if you multiply that by that, well, you basically got a really good thing. So it's 0.73% accurate, or sorry,
0.75.
That's 73.5% accurate, but I know it as a decimal, so that's what I said. Anyway, it's fast and efficient. Hard to find a threshold though, that's hard, so we just didn't classify the things that weren't. We just said everything is in some model, probably. I mean, everybody used to say, I know it is anyway. We attempted to use a code book, but it was slower, we couldn't get it to work. ChatGPT couldn't get it to work, we gave up. So, few perturbations, small images, this is good, this works. If you do perturbation, if you have read the thing, it doesn't work as well. Okay.
Okay, third task. Sorry, we're speed running through this. There's not much to say really. The pain is real. We re-implemented the strategy from the paper that was provided. We tried to get to a decision boundary and then to the tug of war. And at 3 a.m. we were like, why are we here? Just to suffer. It is slow, as I'm sure all of you know. It took us a long time. I think 4 hours got us 2 chimeras. We tried more, but yeah, at the end of the day, we just said, we're going to hack the leaderboard. A chimera is a chimera. Your score function had an indicator. If I use one chimera and plug that in for every single image, the numerator is 1. The denominator will screw me over, but the numerator is 1. So I said, okay, find, for any given image, find out which class it is from. Use a chimera from that class if it is available. If it is not available, use any chimera using round robin, submit it. We got something. It's not great. It's about 3 point something, but it exists. Our experience of the hackathon was mostly like 95% of this, and there's also some other experiences that we wanted to share. But the name, a little bit about the name. We missed a meme over there. Oh, no worries, but go on. You wanted to say something, right?
No, I was just going to say like that, this is my first hackathon, I've done a hackathon before, I know it's so flex. Anyway, the idea is, what I learned about a hackathon, it's like being drunk, like...
It's like being drunk.
You regret it, you say you never want to do this again, but then, the next week you do it again.
I would like to draw your attention to the last sentence on that slide.
Professors are sneaking Thank you so much. Any questions?
Yes, thanks a lot for the quite entertaining presentation. I have one question to your approach for Chimera. So the successful chimeras you found were with the approach from the paper, the tug of war, or did you what was the successful thing?
Right, so we actually did the following. We tried using the approach from the paper and that kind of worked, that gave us 1. The other camera was the following. We said, all right, I'm going to take steps towards the decision boundary and I'm going to overshoot. I'm going to go into the next region. And then I know what was the last step I took. So I divide that step into many small pieces and do this. And basically find out at what point I was in the gap. That was the idea.
And the issue was just that you didn't scale this, so
it wasn't something that we managed to scale and parallelize. Give us more compute, give us a month, we'll give you better results. Maybe paper-worthy.
Any questions from the audience? Okay. So, with that, thank you so much again.
Thank you. Oh, yeah, go ahead.